Let's now talk about samples. If we are able to administer a census every time we need to learn something about a population, that would be great. But in reality, it's too expensive and difficult to execute. And so a sample is a subset of our population. And we use samples to draw conclusions and, in general, infer something about the larger population. So what's important is that the sample that we collect is representative of the population we are trying to infer something about. For instance, if we were trying to, estimate the average height of adults in the US and our sample consisted of only basketball players, that's not exactly a representative sample. And so how we draw our sample affects how accurate the results we end up with are. There are two common sources of error when it comes to sampling, both of which you will become familiar with throughout this course. One of them is chance error, and this is the phenomenon that if we are sampling at random, which we have yet to define, but we will in the next video, if you're sampling at random, the sample that you end up with could look different than the population just due to random chance, and we call that chance error. The other big type of error that you need to watch out for is bias, which is a systematic error in one direction. And so bias may occur when you constantly overestimate or underestimate some quantity. What we will now do is look at a couple examples of non-random sampling techniques before establishing what exactly it is a random sample is. One type of non-random sample is a convenience sample. In a convenience sample, you sample whoever you can get a hold of. This is actually a pretty bad idea when it comes to inference. Haphazard and random are not at all the same thing. Random is one of those funny words where the way we use it in conversational English is very different than how it is used in mathematics and statistics. The term random, for our purposes, has a very specific meaning, and so for a sample to be a random sample, it needs to satisfy these very specific criteria. Convenience samples don't satisfy any of those things, and sources of bias may introduce themselves in convenience samples in ways you might not even think of. And so this example over here on the right is a really interesting one, and once you understand this example, you will understand the issue with convenience samples. And I think this one is really cool, and Professor Adhikari brought this up in lecture last semester, and that's where I got this from. Suppose you have a cage of mice, and each week you want to track the weight of these mice. And let's just pretend we have way too many mice to be able to get the weigh each one of them every week. And so what we do is at the end of the week, we take some sample of these mice, we grab some of them, and weigh them. Do you expect the weights of these mice to be representative of all of the mice in our cage? So we're grabbing a couple mice at the end of each week, weighing them, and do you expect that those weights are representative of the weights of all mice in our population? I'll let you pause the video and think about this, because the result is pretty interesting. Did you pause the video? Maybe, maybe not, but let's pretend like you did. The result was, when people ran this experiment, was that the mice that they sampled each week were consistently heavier than all of the mice in the population. And you might be wondering, why is that? I just grabbed some random mice at the end of each week, and why should they be any different than all of the mice? And it's because, from the human perspective, we're just grabbing arbitrary mice. But from the mice or mouse perspective, if you see this giant hand coming down towards you, what you're going to do is run away from that hand. And so the mice that are, smaller, lighter, and quicker are able to run away from the hand, and then the mice that are heavier are the ones that are stuck being grabbed by this hand each week. And so the weights of the mice that they happen to sample each week were heavier on average than the general weight of all of the mice. And so this is something that isn't immediately obvious when you set out to do this sort of sampling, but these are the kinds of things that may manifest themselves when doing convenience samples. So at the end of the day, convenience samples are not random, and they are a bad idea. What these researchers really should have done is label each of the mice, and at the end of each week, shuffle the labels and then take the first however many that they wanted to sample. And that way, the mice that they sampled each week would be representative of the larger population of all the mice that they had. Another type of suboptimal sampling technique is a quota sample. Now, in a quota sample, you first specify your desired breakdown of various subgroups and then reach those percentage targets however you can. So, for example, you may be wanting to administer some survey to Berkeley undergraduates, and you might say, hey, okay, well, I want 30% of my sample to contain sophomores, and I want 30% of them to contain 30% of them to be juniors, and so on and so forth. And once you establish those targets in a quota sample, you just go out and find 30% sophomores and 30% juniors however you can. And in that way, it's almost like a convenience sample. There are two big issues with quota samples. One is, however you can is not a precise formulation of how to create a sample. It's not a random sampling technique, and I know I keep mentioning this term without having defined it, but trust me, quota sampling is not random because we are not following the specific processes that make it a random sample. The other issue is that by setting quotas, you require that your sample looks like your population, but only with regards to these criteria that you went out and defined in the first place. So maybe it's true that 30% of undergrads at Berkeley are sophomores and 30% of them are juniors, and let's say you happen to capture those percent breakdowns in your sample. But the rest of your sample, we have no idea what it looks like, and for example, you might have a complete gender imbalance or a complete race imbalance in your sample that you failed to account for because your target was to get sophomores and juniors at these percentages and not get an overall representative sample. So quota sampling, for these reasons, is also not a good idea. The issue with both of these sampling techniques is that we need to ensure that our sample is representative of the population. And I just gave examples for both convenience samples and quota samples where that can easily not be the case. One thing to stress is that just getting a big sample is not enough. And that's something you often hear. Well, it doesn't matter if my sample is inaccurate. If I just sample enough people, on average, it should look like the population, right? And that's just not true. And this is a phenomenon that you will explore in homework 2 of this class, where you will perform a post-analysis of the 2016 US presidential elections. And the result is very, very cool. But in general, what you need to know is that just having a big sample doesn't actually make your sample good. And in the next video, we will start off with another example, in addition to the 2016 US presidential elections, where a big sample wasn't necessarily a good sample.